particularly pay attention to Chris's audio if we need to turn it up again.
Okay.
All right, hello everyone. My apologies for us being late. This is Matthew. We had some technical difficulties we were troubleshooting. I think we are all ready to go at this point. Thank you again for joining us. I'm going to hand this over to Chris, who's now back with us in the country.
Yes, welcome everyone. End of my sabbatical back in Tucson, in time for monsoon, heat and humidity. We'll cut to the chase and get right to your questions.
All right, the first question we have is from email, and the question is, I've heard that there is some controversy about the value of the Hubble Constant. Can you talk about that and why it has changed?
Yes, the Hubble Constant is it's the character capital H with a subscript 0, and it's a fundamental cosmological parameter. It's essentially the expansion rate of the universe. The subscript 0 means the expansion rate at the present day, so right now in the nearby universe. So it's a fundamental quantity that obviously relates to the age of the universe, because the inverse of the Hubble constant, if the universe were expanding at a constant rate, is the age of the universe. And there had been historical controversies where the Hubble constant had a range of a factor of 2 depending on what method you used, and different research groups in the 70s and 80s disagreed strongly over the value. One camp held that the Hubble constant was about 100 kilometers per second per megaparsec, and the other that it was 50 kilometers per second per megaparsec. The units tell you what the Hubble constant is measuring. Kilometers per second per megaparsec means for every megaparsec, or 3 million light years in distance from the Milky Way, then that's the number of kilometers per second of redshift, or recession velocity, a galaxy will show. So a higher Hubble constant means a faster expansion rate.
We're not straight.
Oh, okay.
Sorry. I don't know what's going on.
We maybe should punt to another day at this point, because I'll have a collision with another meeting at some point.
It's weird, like the YouTube thing says.
Oh, it's live now, but it's like really small.
Okay, we seem to be transmitting a picture, so we're going to still kind of mess with things and see if we can get it to look better. But it does seem like we are on. So I'm sorry that it's kind of up in the corner like that. We're just going to have to deal with it for now, but I think everyone will still be able to hear and see everything that's going on. So
It's
Chris-
postable. Is it postable?
Yep, it's
Video. Video
you know,
wise.
it's going on. Okay, so how's it going, everybody? Thank you so much for joining us. Sorry again about the complicated technical situation that we've been dealing with. I'm going to hand it over to Chris, who's going to
Yes.
say welcome, and he's back in the country.
Yes, I'm back in the U.S. after my sabbatical, and we're starting very late, so we're going to cut to the chase and get right to questions.
All right, Chris. So the first question is from an email from one of our students who asks, I've heard that there is some controversy about the value of the Hubble constant. Can you talk a little bit about that?
So yes, the Hubble constant is the expansion rate of the universe. It's one of the fundamental cosmological parameters, and historically it's been denoted as capital H with a subscript 0, meaning the current expansion rate of the universe at this present time. It's measured in kilometers per second per megaparsec, which means for every megaparsec in distance from the Milky Way, that's about 3 million light years, what is the expansion rate or recession velocity of any particular galaxy. Historically, there was a factor of 2 controversy in the 70s and 80s. Some groups said the number was 100 kilometers per second per megaparsec, and others said it was 50. Using different techniques gave different answers. So it was a very basic disagreement, and a lot of effort was put into refining the measurement of the Hubble constant. And not surprisingly, over time in the 90s, the value came down to the middle of that range in the mid-70s. Kilometers per second per megaparsec. But in the current era of precision cosmology, a new discrepancy has arisen at a much higher level of precision. There's a set of indications of the Hubble constant that come from measurements of the microwave background radiation. So that's a snapshot of the universe when it was young. And that data is so precise that it allows with the cosmological model you to calculate what the current expansion rate would be given the amount of dark energy and dark matter in the universe. And those experiments give numbers that are about 67 kilometers per second per megaparsec, with a very small error on that. Another set of measurements based on local expansion rate, so the nearby universe, give a somewhat higher number, 73 kilometers per second per megaparsec. That difference of 6, less than 10%, is actually significant because the precision of each type of measurement seems to be so large. And this discrepancy has now blown up into what some people are calling a crisis in cosmology. Why should the expansion rate as measured by ancient measurements of the microwave background be different from the expansion rate measured by local measurements of nearby objects like supernovae or bright red giants that are acting as sort of standard light bulbs in the universe? Nobody knows the answer. There have been large meetings devoted to this in the last few years. One answer, of course, is there's unrecognized error in one or more of the experimental groups, and they've just not recognized their systematic error. Systematic error is a big problem in astronomy because you can't do a separate universe experiment. You have one universe to measure. So sometimes you don't know what your errors are, these hidden systematic errors. The other possibility, which is exciting or scary depending on your point of view, is that there's a missing ingredient in the cosmology, that both measurements are right and something else is needed to explain why the universe might have been expanding faster than it should have in the distant past. And some people are arguing that that's the situation, that we need a new ingredient in the cosmology. Nobody knows what that would be, actually. So that is exciting, or it actually indicates a deep problem in the model. So you'll have to stay tuned for this. So the Hubble constant controversy, which we thought had gone away 10, 15, 20 years ago, has now reemerged in a new form at a much higher level of precision. But such is cosmology now that these measurements are precise enough to really point to problems at the 5% level. Ready for the next question?
All right, the next question is from Maxim Zhirov, who's on with us live, who asks, very distant future perspectives are not bright at all for our universe. Could there be something that will be able to prevent our universe from a cold death scenario?
Not that we know of. All the indications are based on measurements of the local universe, the current expansion rate, the presence of dark energy, which indicates the expansion rate is accelerating. All of that points to the fact that the universe is open, to the geometric term for a universe that has negative space curvature, because there's insufficient mass and energy density to cause it to recollapse in the future. It's not even by a small margin. It's really by a large margin that the universe is open or endlessly expanding. So basically we have to face the prospect and the future of an endlessly expanding universe. And after that, it comes down to thermodynamics. Over a period of time in an endlessly expanding universe, coherent sources of energy and organized matter will gradually dissipate and disappear, and the universe will become more disordered, random, and chaotic. It's a bleak prospect, but it's a very, very distant prospect. Ready for the next question?
All right, thank you, Chris. The next question is from Ilsa Martin, who is on with us live, who asks, Einstein was able to publish some amazing insights, some without corroborating data. Is this still possible today to make a claim with no proof?
It is possible in the sense that there is pure theory. So Einstein was a theorist. He was a very astute theorist who paid attention to observational data. In fact, the theory of relativity was motivated by his awareness of the Michelson-Morley experiment from the late 19th century. So he was not an experimenter, but he was very well of experimental data. But theorists always feel emboldened to suggest new ideas and present new ideas without necessarily having experimental corroboration. However, it has to be a physically plausible idea that's motivated by the current situation in the field, whether it's physics or cosmology or astronomy. So yes, theorists do occasionally propose ideas, particles that have never been observed, for example, or new components of the universe that affect the cosmological situation without experimental corroboration. However, to be considered true science, such postulating or speculating at some point has to turn into something that can be tested, can be observed, can be looked for, and corroborated. Otherwise, it's not science, it's metaphysics and philosophy. Ready for the next question?
All right, our next question is from another viewer who is on with us live, who asks, what is the relation of Earth's orbital motion with the appearance of stars in the sky? And why is a sidereal day 4 minutes shorter than a solar day? I don't fully understand.
Right. So the Earth is spinning on its axis once every 24 hours, once a day, while it orbits the Sun in a year, 365 days. And it's the spinning of the Earth on its axis that causes the stars to rise and set, and means essentially we see the whole sky every day. Now, the stars in the sky during the day are there, of course, we don't see them because of the sunlight. So if if the sun weren't there, you'd be able to see the stars doing their full orbit of the Earth. So measuring time by the stars is essentially the time between a particular star being, say, overhead or passing through the meridian, passing through the highest point in the sky, until it does so the next day, 24 hours. That's a sidereal day. That's measuring time by the stars. But if you measure time by the sun, it's slightly different, because that reflects the time between the sun being at its highest point in the daytime sky and it being at that same position the next day. And if you think about it, the Earth is going around the sun, and in each day it goes 1/360th of an orbit of the sun, which is 1 degree, since 365 is almost the same as 360. So the Earth moves 1 degree of angular measurement around the sun. And so that means the Earth has to go very slightly further for a star to rise and set at the same time than it does for the sun to rise and set at the same time, because it's going around the sun. And that difference is 4 minutes, because if you multiply 4 minutes by 360, you get 24 hours, and that's the entire 24-hour variation of the star position over the course of a year. Ready for the next question?
The next question is from Alondra Sola, who wrote an email asking, how do you think people can be more active in astronomy, as in citizen science opportunities? What are some citizen science?
Yeah, the average person who likes astronomy, cares about astronomy, is excited about astronomy, can definitely get involved in citizen science. There's a consortium called Zooniverse, which emerged from an astronomy project called Galaxy Zoo. Galaxy Zoo still exists, and it's a sort of grandfather of astronomy citizen science experiments. But Zooniverse is a larger umbrella of citizen science opportunities, and the website is that word. It's very easy to find, which include wildlife, paleontology, archaeology, anthropology, a large set of disciplines, some life science ones as well. And there's a core of astronomy, citizen science activities. So I would suggest you go to the Zooniverse site and look at the astronomy citizen science projects, and you'll probably find a dozen, 15 maybe at any given time. Some involve galaxies, some involve solar system observations. There's the classic one of trying to scrutinize data from SETI searches, from searches for intelligent signals, from signals from intelligent life forms in the universe. And Galaxy Zoo, the original astronomy citizen science project, also continues because deep imaging has given us hundreds of millions of galaxies, and literally it's impossible to classify them all, even with a machine. So there's a lot of astronomy out there to do. Some of it involves synoptic observations. So there's a set of citizen science activities that involve variable star observations. An example of that, of course, would be the detection of exoplanets by the transit method using Kepler data. So that's another citizen science experiment. There are really very many, and they range in subject matter from exoplanets to cosmology to galaxies to variable stars, really all over. They're well orchestrated. The interfaces on the web are usually very well done. They're very engaging. You can do as much or as little as you want. They can be a time sink if you really get into them. So definitely I recommend you dip your feet into the water of citizen science and astronomy. Ready for the next question?
Thanks, Chris. The next question is from Alexander Ellis, who is on with us live, who asks, I'm preparing to teach the first ever astronomy course at my high school in the fall. What phenomena or theme do you think I should highlight on the first day to excite students about learning astronomy?
Yeah, great question, and I'm glad to hear that. Astronomy is not that common in high schools in the United States. The standards, the sort of national standards, really didn't do astronomy any favors when they were rewritten 7 or 8 years ago. So it's usually the motivation of individual teachers and instructors who care about astronomy to put it into the curriculum. If you want to grab students on the first day of class, probably the best way is, rather than just doing a standard sort of powers of 10 thing, which is what a lot of astronomy instructors do on the first day of class, the nicest is probably just to find something that's happening in real time. So either find some sky event, some naked eye observation possibility that's around the time of the first day of class, or maybe the second day of class. So you're sending students out there to look at something in the night sky. That's a great hook. And then they can report back on that in the class. Or find some event that's happening in astronomy, a major announcement or a news story that's just been released, or a conference where something exciting is being discussed, and send them off to study that, the non-technical version of that, and maybe bring back into the classroom for a discussion. So having something topical for the first day is always a great hook. Ready for the next question?
The next question is from Mohanad Alzarani, who asks, do neutron stars have a habitable zone where Earth-like planets can survive and sustain liquid water? And if so, have we found any?
An interesting question. So neutron stars are not what we think of in terms of exoplanets that are habitable, but it is, of course, we're bearing in mind that, and it's often forgotten even by some professional astronomers, that the very first exoplanets to be found were found around pulsars, which are neutron stars with radio hotspots. These pulsar planets were found in 1993. They predated the discovery of 51 Cygni, the first exoplanet found by the radial velocity method. Now, generally, we don't consider exoplanets around neutron stars or pulsars to be habitable, though the stars are, of course, dead stars. They emit no radiation except maybe feeble radio waves, so no visible radiation. So the only way a planet might be habitable around a neutron star is if it were massive enough to retain an atmosphere that was dense enough to create a warm temperature, say by greenhouse effect, if the atmosphere included a lot of carbon dioxide or methane. So that's really the only way. It would have to be a very particular massive planet, and probably bigger than the Earth, and one that had sufficient dense atmosphere to create a temperate zone such that water could survive. We don't think there are any exoplanets around neutron stars that have these properties. And in fact, the detonation event of a supernova that precedes the formation of a neutron star might preclude any exoplanet persisting afterwards. But we did find exoplanets around neutron stars. It's not yet clear whether those exoplanets were accreted after the neutron star exploded as a supernova and turned into a neutron star, or before. So it's an interesting question, but I think it's a long shot to have habitability around a neutron star. Ready for the next question?
Thanks, Chris. Several people are interested in the current state of the Giant Magellan Telescope. So could you talk about the update for that project?
Sure. Giant Magellan Telescope is an exciting project out of my university, University of Arizona. It's a consortium. It involves the Carnegie Institution, which is really the host institution, since they own or they lease from the Chilean government the land where the telescope will be located in Chile, and they're a lead partner. But the U of A is also a lead member of the consortium at about the 10% level, because we provide the mirrors for that telescope. So the Giant Magellan Telescope takes the largest mirrors that we can make on our mirror lab, 8.4 meter diameter borosilicate parabolas, and it puts them together in one single truss. So 6 off-axis paraboloids and 1 central paraboloid, looking essentially like flower petals from above, into one coherent telescope with an effective diameter of about 22.5 meters. Incredibly large telescope, will be the world's largest when it's commissioned. Commissioning is actually expected to start in a couple of years. At the present time, 5 mirrors have been cast. The last one is still being polished. 4 have been accepted, and the last 2 are scheduled for the next couple of years. The telescope can be built with a minimum of 4 mirrors, so not the full 7, and first light will involve those 4 mirrors, a significant fraction of the total collecting area, probably in the year 2022, and probably with the full telescope at around 2024. The Europeans are progressing pretty fast with their large telescope. The Hawaiian telescope is on a hold because of controversy in Mauna Kea, and those are the 3 big telescopes that are coming online. But the GMT, Giant Magellan Telescope, with a total capital cost of about $1 billion, is doing very well and is on track. Ready for the next question?
Okay, another live viewer has a question about the recent black hole picture. The picture of a black hole has finally been taken. Will we see more of these pictures? Will it be possible to take a picture of a black hole in its calm state?
Yes, the picture that got enormous press coverage a few months ago was of M87, a giant elliptical galaxy in the Virgo cluster, a distance of about 60 million light years, with a very massive black hole, about 6 or 7 billion times the mass of the Sun. The next picture that's undoubtedly going to be released by that consortium, the Event Horizon Telescope, is probably the galactic center black hole, so the black hole nearest to us, which is only 26,000 light years away, the center of the Milky Way galaxy, and much smaller, 4 million times the mass of the Sun. So we can expect that image to be released possibly by the end of the year. After that, it gets harder. There's a handful of other nearby active galaxies where the black hole image could be made, but it won't be as good as those 2 examples. And then it does get harder. There are, of course, black holes in galaxies that are not active. M87 is active. It's putting out electromagnetic radiation from gamma rays to radio waves. There are many more black holes that are inactive. Essentially, every galaxy is a black hole, which is the state of the one in the Milky Way. And so the Event Horizon Telescope will try to take images of some of those too. But it's really quite challenging. It's going to be working at its limits to get pictures that even approach the quality of the one that we saw a few months ago. Ready for the next question?
The next question is from Jay Ratcliffe, who asks, another supermassive black hole was just discovered, estimated to be 40 billion solar masses. Is there a theoretical limit to the size or mass of a black hole?
That's a good question. That is an incredibly massive black hole, and the mass estimates of a single black hole that far away are uncertain. They can be uncertain by a factor of 2. So when we say 40 billion, it might be 20, 25, or even higher. There is essentially a practical, there's not a full theoretical limit, but there's a practical astronomical likely upper bound to black hole mass based on the most massive galaxy. Because so far, we found galaxies in black holes in galaxies whose masses scale with the mass of the old stars in the galaxy. And there is a maximum size of and mass of galaxies based on the formation theory of how galaxies form in the early universe. Giant ellipticals are the most massive galaxies, and this black hole was found in essentially the most massive giant elliptical we could identify. So since there are no more massive galaxies than this, it's unlikely there are going to be more massive black holes than this. So this may actually be the record holder for some time. Ready for the next question?
All right, Matt Springer sent an email and is interested in time dilation in special relativity. In particular, he would like to know how it works that if an individual is traveling in one direction very fast, close to the speed of light, and another individual is traveling in the opposite direction, say at the speed of light, that both of them are justified in saying that their clocks are moving, the other person's clock is moving more slowly. But how can it be that both clocks appear to be running more slowly?
So it's probably in the situation of relative motion, it's kind of arbitrary to say that each clock is in motion. Really, all that matters is the relative velocity or speed between the two observers, the two people with clocks. So there's only one velocity difference in the motion. And so that translates into one time dilation number, just plugging into the equation of special relativity. And by the reversibility idea that there are no special observers, it's a symmetric situation. So the inference of slow time from one observer relative to the other also holds in the reverse perspective. So they're not two separate situations. There's just one situation based on the difference in speed of two observers relative to each other. And because it's symmetric, the same dilation is observed by each observer. Ready for the next question?
Okay, the next question is from one of our live viewers, Maxim Zhirov, again, who asks, there is recent evidence that life on Earth existed even before 3.6 million years ago, or billion years ago. Could it have emerged right after the formation of our planet?
Yes, the age of the oldest life on Earth is a somewhat controversial because the evidence that we're looking at is very fragmentary. Life was, of course, small, microbial. It's very hard to find unaltered rock from before 3 billion years ago. So the current evidence is pretty strong that microbial life existed at 3.6. It's not bad at 3.8, and around 4 it starts to get more shaky. But there are some people who claim that the Earth was habitable substantially before 4 billion years ago. The oldest rock we know of, a zircon crystal dated to 4.4 billion years, which is very close to the formation of the Earth, was apparently formed in an aqueous temperate environment. In other words, there's a tiny little chip of zircon that's the oldest rock we know of on Earth that indicates that the Earth was habitable. Now that's not at all the same as saying that you found life that long ago, but it's also not saying that life couldn't have existed. Finding evidence of life before 4 billion years ago is extremely difficult. There's essentially only 3 places on the Earth's surface where you can find rocks older than that. I think one is in West Greenland, one is in South Africa, and one is in Western Australia. And people go to those places to try and find very old rocks. But the evidence for life that long ago is extremely hard to pin down, and it's essentially always very controversial. So it's possible we may never know if life on Earth existed before 4 billion years ago. Ready for the next question?
The next question is from Anthony Lin, who sent a question via email. And Anthony asks, the expansion of space-time results in redshifting of electromagnetic waves, but what happens at infinity? Could an EM wave lose its waveform so much that it becomes a straight line?
In an infinite, redshift is only possible in principle and in theory. It's an asymptotic value, and so yes, if you extrapolate expansion speed to an infinite speed, you infinitely redshift a wave, and you reduce its wavelength, you reduce its energy to zero, and its wavelength becomes infinite. That's an extrapolation, but that's probably not happening in practice. Now, in the far future of the universe, if dark energy continues to make space-time expand at an ever-accelerating rate, then the microwave radiation that currently is at wavelengths of sort of millimeters to centimeters will stretch to meters, kilometers, thousands of kilometers, and so on. So that what you're asking about in the question will actually happen to the microwave radiation left over from the Big Bang in the far future as the universe expands faster and faster. And yes, I guess if you play out the infinite future of an ever-expanding universe, that radiation would end up with zero energy and infinite wavelength. Ready for the next question?
All right. The next question is from a live viewer who asks, could our universe be a giant black hole or left over from a black hole? So what could be the possible relationships between the Big Bang and a black hole?
So some people have noted that the Big Bang has some of the qualities of a black hole. That the universe, for example, can have something akin to an event horizon. The universe doesn't actually have an event horizon. An event horizon is a boundary around a massive object from which nothing can escape, not even light, and certainly not matter. Now, in principle, an expanding space-time universe can be bounded by a horizon. It's not formally an event horizon, but it's the same idea. There can be a region beyond which no information has reached, nor can reach, maybe in the future. And so in that kind of simple sense, an expanding universe can be analogous to a black hole. But in the end, it's really quite different, because a black hole is a static situation of intense gravity and space-time curvature. An expanding universe, is a dynamic system of gravity and space-time curvature. And so, we can't push the analogy too far. Ready for the next question?
All right. The next question is from Jan Campos, who asks, I'm reading your book, Einstein's Monsters, and in it you write, the universe is governed by general relativity and not special relativity. So space can expand faster than light. But he would like some clarification on what that means.
Right. So the restriction on light being the fastest thing there is based on special relativity, which is the idea of looking at how signals, light, information, particles travel in space-time on small scales, where you can define essentially a grandiose lab experiment to measure how signals travel. The universe is made of expanding space-time, and the expansion of space-time in the current cosmology is governed by general relativity, and it's described by general relativity, but general relativity does not specify a speed limit for that space-time expansion. It's a matter of observation. The theory fits our universe, but to know how fast space-time is expanding, we actually have to observe it. The theory does not dictate it. And since that, and because of that, the theory does not contain a speed limit for the space-time expansion. So it's entirely possible in general relativity for any 2 points in space-time to be moving apart faster than the speed of light, because the space-time itself is expanding. It's not a signal transmitting situation. You can transmit signals within the expanding space-time, and they might never reach their destination if the space-time is expanding faster than light. And that, in fact, was the situation early in the history of our universe. So the real reason why faster than light space-time expansion is possible is because general relativity does not include any limit on the speed of space-time expanding. It's a matter for us to determine by observation. Ready for the next question?
All right. My apologies, everybody. We are aware that the video is cutting out, but we're going to continue with audio. We have about 10 more minutes, so we'll just keep going and see if we can fix the video. But for now, it's more like a podcast. So the next question is from a live viewer who is wondering if you have any recommendations for news channels or media sources where he can get or she can get current events about astronomy and find out about astronomy news?
Yeah, I mean, space.com is the standard source of information. Has a lot of things about space program and aviation and space travel and space flight, as well as astronomy. Some people find space.com to be a very ad-heavy environment, and they don't like it for that reason, but there are a lot of good stories. Science Daily is one I recommend. It has science stories across all disciplines, and the astronomy feeds typically feature several stories a day, and they're related to news releases from universities, so they're very well written, and they often have links to the technical article if you want that. So those are two good sources if you want basic information about what's happening in astronomy from day to day or week to week. Ready for the next question?
All right, thank you, Chris. I think we are fixing the video, but we'll see in just a couple minutes. So the next question from a live viewer is from Yuna, who asks, if you know about where are good places in Europe to study if you want to study astronomy. What are some good colleges in Europe where you can specialize in astronomy?
Sure. So Europe, like the United States, has astronomy programs. Astronomy, of course, is often academically considered an offshoot or a cousin of physics. So you're most likely looking for strong physics programs to find an astronomy program. And many universities will do astrophysics as like a specialization of a physics degree. So you're not actually getting all astronomy all the time. So the standard places that are good for astronomy are often the places where the research in astronomy is good. In the United Kingdom, that would be Oxford and Cambridge, Imperial College, Birmingham, Glasgow, most of the major universities that have strong science programs. In continental Europe, Munich is a good program. Heidelberg is very strong in astronomy. In Italy, Rome has strong astronomy and also space science. And in Holland, which has a strong astronomy history, as a small country, it's sort of punched above its weight, if you like, in terms of astronomy. Leiden is a big astronomy program, very important, and probably the best one if I was just to pick one. So there's a selection. Germany, Italy, Holland have the biggest and best astronomy programs, along with the United Kingdom. Ready for the next question?
All right, our next question is from email, and the writer asks, I'm sorry, I got a little bit lost here. Can you talk a little bit about why retrograde motion occurs? There are lots of talk, people talk about it all the time with regards to planets and horoscopes and things like that, but can you explain why it happens?
Right, so in terms of solar system dynamics, prograde motion means an object that is spinning or rotating in the same sense as the object that it orbits. So that would mean a planet that spins in the same sense as the star that it orbits, same angular momentum vector, if you like. And for a moon of a planet, it would be the same thing. It would be a moon that's orbiting in the same sense and direction as the planet that it orbits. And that's the natural way an orbiting body like a moon around a planet or a planet around a star will behave, because that's how angular momentum is dictated, since these objects were formed out of one gas cloud a long time ago. It's natural that they will share the orbital motion and therefore the angular momentum of the original gas cloud. Retrograde means the opposite. It means obviously that an object, a moon or a planet, is rotating in the opposite direction to the object that it orbits, and that's a little counterintuitive and it's a little unphysical. So usually you have to propose some mechanism by which the retrograde motion has been put in place, and usually in astronomy that involves a collision, an impact, an intervention by an outside object far ago in the history. And so for Venus, for example, which is the counter-rotating planet in the solar system, we assume there was a major collision early in the history of the solar system. So retrograde is unusual, and there has to be a mechanism to induce a retrograde motion. And it's usually caused by an interaction with another massive body from outside the system. Ready for the next question?
All right, the next question is from Jay, who's on with us live, and asks, are there any efforts to find and map intermediate black holes and estimate the number of these in the universe and their characteristics?
Yes, people are trying to measure intermediate black holes. That's a difficult category to detect. Intermediate mass black holes essentially mean masses between a few tens of thousands of times the mass of the Sun and a few 100,000 times the mass of the Sun. The Milky Way has a 4 million solar mass black hole, so that's where sort of normal galaxies kick in. And these intermediate mass black holes are either going to be found in the centers of dwarf galaxies, or probably in the centers of globular clusters orbiting within galaxies. They're very hard to find because the low mass means their influence on the surrounding stars is more modest, and so it's hard to detect them that way. So there's never probably going to be a very good census of intermediate black holes beyond the Milky Way, where they could be found in globular clusters, or very nearby dwarf galaxies in the local group. Ready for the next question?
All right. My apologies, everyone. We're having, again, a little bit of equipment difficulty here. Our camera is giving us trouble, but we still have audio. So like I said, as long as we have audio, we'll continue. We have time for one more question for today. And the last question will be from Bipasha, who is on with us live and asks, adaptive optics and interferometry are both solutions for visible light and radio waves. Is there any possibility that we could use them for detecting gamma rays, X-rays, or infrared?
Definitely. Adaptive optics is already used for infrared. In fact, the detection of black hole in the galactic center was done with near-infrared adaptive optics starting 10 or 12 years ago. So adaptive optics is a mature technique in the near-infrared, which is only a factor of a few longer wavelength than visible light. And however, high energy radiation, it's definitely a difficult problem, and that's because the coherence that you require, you have to measure the coherence of the radiation to be able to use adaptive optics, which means you have to measure the phase of the wave. And for very, very short waves like gamma rays and X-rays, we don't actually have a current technology to be able to measure the phase, and therefore we can't correct for the phase, and we can't use standard adaptive optics methods. So that's sort of beyond the pale of technology right now and for the foreseeable future. It's a good question to end with, and so we'll wrap up for today, and we'll be back with you maybe next week, actually. Okay, goodbye, everyone.